So, a capacitor, and I think we've shown pictures of them in previous lectures, and they come in lots of different shapes and sizes. We're going to first study them in their most basic state, which is parallel plates separated by some distance and nothing in between the plates. But most of the time, in reality, there's always something in between the plates, and that something, besides air or a vacuum, is an insulating material. The fancy name for it is a dielectric, but we'll get to that later. And so what's interesting is you have this insulating material, and insulators don't conduct. Insulators do the opposite of conduct, they insulate. And so capacitors, charge doesn't flow between the plates. Electrons don't jump the gap, all right? But we get circuits to perform various actions, nonetheless, even when there's capacitors in them. So capacitors sort of strain your credulity a little bit at first, because you're like, wait a minute, if they're not moving across those plates, then how is current moving around in the circuit? And so we'll see we'll get over that eventually, later today. So here's when electric potential is applied to a capacitor, electrons move from the plate of the capacitor, or from the plate closest to the positive terminal of the battery, which pushes electrons from the negative terminal, and we're going to do a demo here in a second, of the other plate. Now, I'd like to do the demo inside of this recorded lecture, but the simulation is not yet an HTML5 simulation, so when I embed the browser, it won't work. All right? At least on my iPad, it won't work. So I'm going to pause. Most important thing, well, a very important thing, electrons do not jump the gap. Or if they do, you just ruined the capacitor. Okay? You can spark a capacitor just like a little lightning bolt, but that takes an enormous amount of voltage to break down air and have it actually discharge things. So that's that. Now, let's get to some math here. So, capacitance, whoops, that's the wrong color. Fix all my colors here. So, capacitance which we use capital letter C. Yay, we finally use a letter that makes sense. All right, so it's defined as, if we were to write an equation, we could write charge, or capacitance equals charge per unit change in electric potential, or change in voltage, the voltage. Difference between 2 points. And the unit is defined as the farad for Faraday. Remember him from the movie? So among other things, he's the one who kind of defined capacitance and found the patterns that we're going to pay attention to. And so, hence the unit's named after the person who figures it out, gets the unit named after them. Newton figured out force, so he got the Newtons. Faraday did capacitance, so he gets Faraday, or farads. And so, basically, 1 farad is equal to 1 coulomb per volt. Okay? Coulomb of charge, or 1 volt. So that's our farad, big F for farad. So a couple of things to note. Remember our surface charge density. We did this a while back. And we would write that with this sigma was the symbol for surface charge density, and it's just charge per unit area, right? And in a uniform field, which is what you get between the plates of a capacitor, meaning instead of it radiating out in all directions, everything's parallel electric field lines, which you would get between 2 charges, all right? And if you line up a bunch of charges on a plate and put it parallel to another plate, then you're going to get a uniform electric field in there. So in a uniform electric field, you get this, that the electric field is defined as surface charge density per this epsilon naught, this permittivity of free space. So really that just comes out to be Q per A epsilon naught. There's 2 ways to write that. And also in a uniform field, you get voltage equals the electric field times distance, which means you're going to get that surface charge density times the distance between the plates per epsilon naught, or the Q per A, or QD per A epsilon naught. So these are just some formulas that we'll end up using as we go along. Now, if C equals Q per V like we showed above, then that means capacitance would be that charge divided by what we just determined voltage to be. So we have all this QD per A epsilon naught, which means capacitance ends up being dependent only on the geometry of the device. So if you were to start with our definition, okay, the definition, it sure looks like capacitance is directly dependent on charge and indirectly dependent on voltage, because that's what we're used to thinking of when I look at a fraction. If something equals a fraction, that means the thing on the left is dependent directly on the numerator and dependent indirectly on the denominator. But that's a definition, okay? In fact, probably should be more careful and write this kind of triple bar thing, because that means it's defined to be that way. But when we pull it all together, charge and voltage shake out of the mathematics, and you only have capacitance defined in terms of the area of the capacitor, the plates, the separation distance d between the plates, and then this constant that's fundamental to all of nature. So capacitance, which is weird. Well, it makes sense in some way, but then why isn't it dependent on charge and voltage if it takes voltage to get charge moving? All right? You can transfer charge directly just by touching it, I guess, too. But so this idea that it's dependent on area and distance, it's dependent on a length factor, a length dimension, because area over distance is a length unit. It's meter squared per meter. It just ends up being some number of meters. All right? So that's one of the weird things. Physics, science often violates our common sense. Okay? Sometimes it's spot on with our common sense, and other times it's like, what? And this is one of those, what? Just the area of it. Now, on one level, it does make sense because, well, I can only get so much charge on this space. So it does make sense in that regard. But why the capacitance would depend on the distance between the plates, that's not as obvious unless you understand an electric field and its relationship to voltage. Okay? But the only thing that's really obvious is, well, sure, you can only get so much on this area. So that does make at least a little sense, right? So but the idea is capacitance depends only on geometry, and I'll say space itself, because that's what this factor is about. So epsilon naught is about space itself, and A per D is the geometry. So there is this fact that Faraday observed that capacitance increases when an insulator is placed between the plates of a capacitor. Now he was dealing with a spherical capacitor, actually, which is interesting that it all started with basically two concentric spheres of material that he had embedded one in the other as opposed to parallel plates. And so what he came up with is that there's this numerical factor, and we use the symbol kappa, which is a really squatty little k, like a small caps K almost. And this is what we call the dielectric constant. All right, so we're going to be introducing that. And Faraday, he came up with this formula for the spherical capacitor, and it had this 4 pi epsilon naught r. And so that 4 pi r, that sort of makes sense for a sphere because the surface area of a sphere is 4 pi r squared, the volume is 4/3 pi r cubed, etc. And so why the 4 pi comes in there for a spherical capacitor, all right? But so basically what I can write here is in a different sense, we can write this. And so let me just finish the annotation. So this is for a spherical capacitor. We just showed one for a parallel plate capacitor. And really all this L thing is just signifying more simply just a length dimension. Okay? And if you look at it, 4 pi epsilon naught is a number, and then there's this radius involved, so it's a length dimension. So it doesn't matter what the shape of the capacitor is, the capacitance, and this is Faraday's work, so a little history there. And we just use this fancy L to indicate a length dimension. all right? And because that's what that area per distance shakes out to be, a length dimension, all right? And so in using that kappa, since it's just a numerical factor that increases capacitance, because that's all dielectrics do. The simplest capacitor is a vacuum between them, nothing. Air is almost like a vacuum, and then stuff. And so no matter what the stuff is, whether it's air or solid stuff, it always increases capacitance. So K is a factor that multiplies it up, scales it up only. It never scales it down, right? And so we can just have this numerical factor inserted into it. And what he ended up coming up with is that this kappa thing boiled down to related to capacity of air, all right, this capacitance. So this is just kind of taking a little historical journey back on this. Now, let me make a few statements and we can try to sort out. Capacitors kind of, their behavior is weird, which is why I'm laboring the discussion a little bit, because it takes some, and your lab will help you sort it out. Hopefully we'll be able to do that in class Wednesday. You could conceivably do it on your own, but it might go better inside. So let me just type out a few statements here. So the charge Q on the plates increases by the factor K when constant voltage is applied by the battery. So really, what I'm typing up here is really Faraday's observations, okay? And then this next one is about when there is no battery provided and you're just getting charge on the plates by some other means. The charge Q on the plates remains constant in the absence of a battery, thus decreasing the electric potential V, or voltage, between the plates by the factor K. So these two statements that are really just repeats of Faraday's conclusions, all right? So what I want to do now is see how does that work out with our definition, because earlier I told you that capacitance was defined to be charge per unit voltage, which means if I want to talk about the charge, I can flatten this equation, just have Q equals CV, and I'm going to apply that to both of these statements here, all right? So we have a constant voltage, okay, in this first example. And so if the voltage is held constant and you observe that charge increases, then it must be the fact that capacitance increased. So if you just let the battery will only put out so much voltage. It's not like it'll increase its voltage. Okay? If anything, its voltage goes down over time as it loses its ability to recharge. All right? All right? That chemical stuff poops out, so to speak. So we have a direct dependence in this sense where, okay, if I hold voltage constants and I see that more charge goes to the plates, that means by definition the capacitance went up. Those plates had more capacity to hold charge. All right? What if I'm not involved with the battery? Okay, and it's just charge got on there some other way. So now, if that's the case, if the charge got on there and it was isolated from a battery, then that's it. There's no other charge in town. And so total charge will remain constant when there's no more ability to move charge around. So in this next one, the charge is held constant, all right? And so what happens, you notice that the voltage decreases in that case. And the only way that this could stay balanced is if increased capacitance in the non-battery case means a lower electric potential. Something's got to give. In the previous example, the battery kept giving, okay? And it kept voltage constant, which means the other two things had to change in a fashion that made sense. So if one thing went up, the other thing had to go up when the battery was involved. But in the second one, it's impossible to maintain constant voltage. You're stuck with constant charge, which means the other two have to, what the one does, the other does the opposite of, okay? But in this second one, it actually matches. If I look here, if charge is held constant and voltage goes down, then capacitance has to go up in that case. And the same is true here. Just looking at that one, if voltage is constant and charge went up, then capacitance had to go up. Doesn't matter which way you look at it mathematically, it all shakes out the same. Now I want to try and show what happens when you put stuff. So I'm going to make two parallel plates. And if I charge them such that there's a bunch of pluses here and a bunch of minuses here, and let's put some molecules between them. And so, we have two kinds of capacitors, and this seems silly to say, and some of the dielectrics are polar, meaning they have dipoles. They have permanent dipoles, and then there's ones that are nonpolar, which means they don't have permanent dipoles, but any material, you will polarize the molecules. Whether they come that way or not, you put an electric field on them, they're going to start polarizing. Their dipoles are going to start lining up, all right? So what happens in this case is all of the minuses want to go near to the plus end, and all of the pluses want to go near to the minus end. So what this means is initially, we had an electric field that went from the positive plate, so our initial electric field, E sub 0, was the field that would go from all the plus charges on the left plate to the minus charges on the right plate. But we get an opposing field due to all of these dipoles. We can call this E sub D, because the electric field of each one of those molecules kind of goes the other direction. And so what that means is you have a net electric field that's the difference. So you literally have your final electric field is going to be the initial electric field minus the induced electric field due to your dipoles. So when you do this, the capacitance goes up even though the electric field between the plates goes down. Okay? And so that's a dielectrics weaken the electric field. And in fact, Coulomb's law for a capacitor with dielectric, you still have your 4 pi epsilon naught and your Q per R squared, but you have that kappa factor thrown in there. Okay, but you always have, when you're dealing with dielectrics, there's always this kappa thing, epsilon naught. There's always a piece of that puzzle. And by the way, kappa for a vacuum is 1. So if you're dealing with a vacuum, you just get Coulomb's law back, unscathed. So that's that. So one more little piece of this puzzle. We break to some examples. So we define, this dielectric constant, after all of those considerations, so we're kind of retracing Faraday's steps as best we can in a short amount of time, because we don't want to take as long as he took, ends up being definable as just the new capacitance over the old capacitance. And for C just equals Q per V for a dielectric material, and C naught per QV naught for no dielectric. And what that means is that your ratio of new capacitance to old capacitance is inversely related to voltage and electric field. Whoops. I got a little scrunched over there. So, where is this going? So, if we take that kappa and deal with the electric field like we were just paying attention to, kappa in terms of the electric field, so I can talk about kappa in terms of capacitance or voltage or electric field. I'm choosing electric field because we've already been talking about that capacitance, and I want to bring it all the way back to what we started with. So what this means is that my electric field, the final one, that's all we're always concerned with, can be written as, here is the electric field that you'd have for a capacitor that has air between it, written this way, which means if I throw in what E is defined to be, which is Q per, normally it's just Q per charge per unit area, epsilon naught, but it also has that kappa in there, okay? Because that comes from what we started with here. And this just breaks down to, and here's where the little sleight of hand goes. What I've done here is this kappa epsilon naught can just be written as epsilon for a dielectric. Now, let's talk about this briefly. So, epsilon naught is the electric permittivity of free space or a vacuum. And one more time, what the heck is that? That's the ability of space to tolerate an electric field. Or at least that's an oversimplification of it. It's really space's quote unquote capacity to have electric fields in it. This is the way that we quantify how space lets charges do its thing, do their thing, okay? And so what we have here is it's literally the case that just epsilon with no subscript is a dielectric constant times the permittivity of free space. And if you're talking about a vacuum, kappa is 1, and your dielectric constant is the permittivity of free space. But if you're not in free space, meaning you've put something in place of a vacuum like air or plastic or whatever, then now you're using a modification of this fundamental constant of space. All right, so that's the difference. So we have to use these equations, and it helps if we can understand at least a little bit about them. So that's why we bother. So to wrap this little piece of the pie up, so we've worked out the electric field for a capacitor is Q per epsilon A, and that's good because capacitance was dependent only on area and distance, and now the field is still dependent on area and the charge, but fields are defined in terms of charge, so we couldn't lose that. Coulomb's law has to still factor in. So we had this other equation before. Voltage is electric field times distance. So if I take the electric field that we just worked on and put it into together with this other thing, then we have that, and then one more layer, take capacitance, which we defined initially as charge per unit change in electric potential, and then take this new thing in. And so we're going to end up with K epsilon naught area per distance, and that's kappa times the C in air, because that takes us all the way back up to here. So once again, it's still the case. Capacitance is still dependent on the geometry of the device itself. All right, so let's be honest. I just took on a little mathematical proof journey, and you're like, okay, what the heck is good as that? What this does is if we define, we have it, so Faraday had an observation. So this is, one of our objectives is your understanding of science. And so not only is that an objective in every science course, but the college itself has learning outcomes, and one of them is ability to just generally get science. So Faraday had observations, he made a definition, made up capacitance. And so, and capacitance seemed to go up if you did that, going down if, voltage, all these relationships. And so what you have to do in science is, okay, I have this pattern, seems right. If I go the full distance, if I connect it to the known laws, I have to be able to get back to what I started with. And if I get back to what I started with, and that means that this new thing I've invented that was related to old things that were established is consistent with the laws of nature. And so what we did was a really fast whirlwind tour of take Faraday's observations and then do the math and go, yep, along the way I keep getting back Coulomb's law when I shake the tree hard enough, and I get back to where I started by leveraging known laws. So I obtain the known laws along the way, even with modification, and I get back what I started with. And if none of the math is wrong, then I have a consistent system. My reasoning's correct. That means I can trust the empirical results and I can make predictions. This is now used, we've verified that it's usable. So these new versions of capacitance or electric field will now apply to this special case of capacitors. It won't apply when it's just single point charges. That's when we just use Coulomb's law plain. So you have all these variations that come with changes in geometry. So that's the idea. Now you don't have to, it's not going to be on your test, but it is part of our game here. All right. So now, for something that is different, we're going to start to pay attention to capacitors and circuits. And so if I build me a circuit that has a battery, and the way we draw batteries is with these different sized bars, and you have the big bar is always your plus, little one's always your minus, and we label it a capital V because it's a voltage source. And then we're going to connect that voltage source to something, and in this case we could have a capacitor, we could have multiple capacitors, say in parallel. And so in this case, these capacitors will all have the same voltage. All right, so for instance, if you, in this room, we have 4 rows of lights. Each one of those lights is on the same voltage. They're in parallel. In fact, you're looking at them and they're literally parallel to one another physically. And that's because the circuit up in the ceiling or wherever is arranged kind of like it is on screen here. Instead of lights, we're dealing with capacitors, but they're in parallel. And then every circuit in this room is hooked to the same voltage. So a lot of parallel circuits. Some of these things are in series, like some of these outlets are in series, all right? But some of those series outlets are parallel to one another, parallel to the lights. They're all feeding off the same voltage, and you can have any number of things in a line, but then all of those lines can be literally parallel to one another. So each one of these capacitors feels the same voltage, right? So this is a parallel circuit. So 1 voltage throughout when it's a parallel circuit, V, because there's only one electric potential hooked to everything. And so we should recall, since we just built this, we have this equation that says capacitance is Q per V, charge per unit voltage. And what that means is that any particular amount of charge, which we could call Q sub I, would be equal to the capacitance at that location and the voltage. So that means I have, at the C1, I'll have charge 1 is going to be capacitance 1 times voltage, since there's only one voltage. The charge on capacitor 2 will be its capacitance times that 1 voltage, and the charge on capacitor 3 will be its capacitance times that voltage. So we have these 3 ways to talk about the charge on these individual capacitors, and just like Faraday noticed, when I have a battery, the voltage is going to be constant, all right, on whatever load it's applied to. So this means that, so the sum of all of the little charges is going to be the total charge. We add up all the charges. And so if I just come in here and say, all right, well, this is going to be Q1 plus Q2 plus Q3, which is necessarily going to be capacitance 1 times the voltage plus capacitance 2 times the voltage plus capacitance 3 times the voltage. Right? So this means that my total charge, notice that voltage is common to all of these things. So I can pull out the sum of the capacitors times the voltage. So what this is here, this is an equivalent capacitance. In other words, I have two choices. I could have a circuit with 3 capacitors in parallel, or I could turn, since it works out to be under the definition of capacitance, which is all this Q equals CV, is just a rearrangement of the definition of capacitance, which we just proved to be consistent with Coulomb's law, etc., etc. So that means when capacitors are put in parallel, their capacitance adds up. And so what I could have is I could have Q equals an equivalent capacitance times that voltage. So let's say that those capacitors were 5 nanofarads each. I could, instead of having 3 5 nanofarad capacitors, I could have one 15 nanofarad capacitor, and I would get the same result. Right? Or if it was a 2, a 3, and a 4 for C1, 2, and 3, I could just change it out to a 9. 2 plus 3 is 5 plus 4 is 9. Right? So we're going to do, this is sort of setting up for spring break, but really this is charge conservation. All right? The sum of the parts has to equal the whole. Charge, you learn that energy is conserved, momentum is conserved, charge is also conserved. All right? So this is really a charge conservation thing that we will end up using extensively when we do our circuits. Because when we do circuit analysis, we'll have various things in series and parallel. We'll have resistors in series and parallel, we'll have capacitors in resistance and parallel. And so our math changes a little bit when the configuration changes. We've seen that a bunch of times too. All right. So that's what a parallel set would look like. But why put them in series? Great question. Glad you asked. So if I have my battery so we have our voltage once again, that's plus and that's minus. C1, C2, C3, etc. So now we have to have the same charge everywhere because there's only going to be one path for current flow. And that was what I was trying to show in the other simulation before it died on us, is how the current flow was the same everywhere. So we'll have to redo that some other way. But so let's just try to think through this. So this voltage is going to start, it's going to get current moving, it's going to get charges moving. And what will happen is you're going to get these charge pileups here. And since there's only one path for current flow, every capacitor is getting the same current flow, and that means every capacitor has the same amount of charge on its plates. I don't think that's obvious, which is why we're giving a pause to that fact. And so once again, okay, so well, let's this is a series capacitors. All right. So we still have this C is Q per V, but we are no longer dealing with the charge is the same everywhere, okay? But the voltages aren't necessarily going to be the same. So what I have here, I'll put change in voltage. So my change in voltage total is going to be the sum of the voltages. So I'm going to write this and then try to say something about it. Thinking back to the water tower analogy, all right? The battery is this huge water tower of electrons. And gravity, if I open the valve, and the valve's open in the circuit, then electrons are going to start flowing with whatever force is consistent with how big a water tower, how high up it was, how much water was in it. Bigger the tower, higher the tower, faster the flow, more flow. So it's going to start going through these parts of this circuit. And if capacitors 1, 2, and 3 are the same capacitance, then the voltages will be the same. Okay? But if one is bigger than the other, then they're going to have a different potential across them. Okay? So it'd be like, well, you've been to a water park. So you could have a really high slide with multiple loops in it, or just one big drop. And so your potential for speed is bigger if it's just one huge drop than it is if you have drops where you go down and then up and you kind of lose, stuff like that. So same idea here. Now, these we could pretend just for simplicity that these are all identical, so that means these voltage drops will always be the same. But in the last one, voltage was the same necessarily. Voltage is not necessarily the same here. Voltage would only be the same here if the capacitance was the same. If the capacitance is not the same, then the voltages will not, the individuals will not be the same. They all have to add up to the overall voltage, but they don't have to be the same unless the capacitors are identical capacitors, all right? So that's why we're, instead of doing a sum of charges, now we're doing a sum of voltages, which also conserves energy. So we did charge conservation in the last one because that was the nature. We had a constant voltage. Now we don't necessarily have a constant voltage per device. We had a constant voltage per device in the last one, right? Well, these voltages, this right here, change in voltage would be Q per C. All right? So now we're going to have Q1 per C1 plus Q2 per C2 plus Q3 per C3. However, Q1 equals Q2 equals Q3, or we could just say it equals Q, because since there's only one path for current flow, the current flows the same everywhere. All right? And so that means I have a constant in here. I have a Q that comes out of everything, and what's left behind is a 1 over C1, 1 over C2 plus 1 over C3. All right? And so our change in voltage ends up, the total voltage ends up being, now again, this is now our equivalent capacitance, which is harder. Okay, so if these were all 5, if I had a 5 and a 6 and a 7, or a 1 and 2 and a 3, then I'd have to whatever half plus 1/3 plus 1/4 is, or whatever those values are, add all that up, and that's my new capacitance. Okay, and so the equivalent capacitance is smaller than the smallest. That's the way this works out when it's in series. Now what's interesting is resistors are flipped from this. Series resistors add, parallel resistors have this 1/over property going for them, right? So this works out to be, we can just write it as charge per the equivalent capacitance is what we would get when we put these things in series. All right? So just some preliminaries. Now let's apply this. So let's start with a circuit, and this circuit it's got these 3 in parallel, and then we have the nerve in mitigated gall to branch off like that, and all of this is going to be connected to a battery. So capacitor 1, capacitor 2, capacitor 3, capacitor 4, capacitor 5. This is our battery. So what we can do, and again we're setting up for the analysis, sooner or later we have to do this sort of analysis. What I can do is I can go, you know what, this parallel network, we just figured out what its equivalent capacitance is. We just did a 3 in parallel before we did the 3 in series. And the thing is when I have a parallel network, and so this little part of the overall circuit is a parallel chunk. So I can say, all right, I can convert that to a single capacitor. So that's what we're going to do. And so the capacitance, I could call it 1, 2, 3, will just be the sum of those capacitors, because we just worked that out. When they're in parallel, I just add them. So now I know that part. So then my new version of this, I could write it as a single capacitor, which I'll call C123. And that's going to be in series with C4, in parallel with C5, and then I still have my battery out here. So what we did, what these formulas let us do is simplify or reduce the size of the circuit. So the corollary to this, in your last experience in math class, you would have learned systems of equations, and you end up kind of boil it down to get to one thing, and then you get to take that value back and reuse it to expand it back out. We're essentially doing the same thing. And in fact, some of our circuit analysis after spring break will actually involve systems of equations. But this is the partially easier side of this. Now, the next thing I can do, okay, is I can't really deal with these in parallel right now because this equivalent circuit I just made is now in series with something. So before I can deal with C5 being parallel to anything, I've got to convert these things that are in series to a single capacitor instead of 2. And so that rule that we had said that when I add these, so my 1 over C1, 2, 3, 4 will be 1 over, whoops, need to put an equal sign in there, will be 1 over C1, 2, 3 plus 1 over C4. That's applying that other rule that had the fractions. All right, and so this one actually works out to be, and hopefully this will make sense, what's the common denominator going to be between C1, 2, 3 and C4? Well, it'll be their product. All right, and so what you end up getting is when you flip it all over, you'll get a product C1, 2, 3 times C4 over C1, 2, 3 plus C4. Okay? Skip the... Because what you would get before that step would be C4 plus C1, 2, 3 over their product, and 1 over, you flip it both over, and you get what C1, 2, 3, 4 equals. All right? So now, part C, so we went from A to B, and now we'll go to part C. I can reduce this circuit one more time, and I'll have C1, 2, 3, 4 in parallel with C5, and all of that is now parallel to our battery. So now that big circuit keeps shrinking down to something smaller. And in our next one, well, all we have to do is add these. So C1, 2, 3, 4, 5 will just be C1, 2, 3, 4 plus C5 because they're parallel. So we only have two options. Either we're adding them simply, arithmetically, or we're adding them in their inverses, which can get more complicated. And so the final version of this circuit would just be a single capacitor in parallel with the battery, okay? And this capacitor is our final C1, 2, 3, 4, 5. The equivalent of all the above. Okay? Now what's that going to look like? Well, I'm going to have to create a new page, but you have it all there, so you don't have to bother with it. But the final, I'll have to be more conservative with my space in the future, all right? But C1, 2, 3, 4, 5 would be the same as C1, 2, 3, 4 plus C5, and we found that C1, 2, 3, 4 was C1, 2, 3 times C4 over the sum of those two factors, and then we have C5. Well, what was C1, 2, 3? Told you we'd backtrack. C1, 2, 3 was just the sum of C1, C2, and C3 because that was a parallel network. And so finally at the end here, well, I guess that really is about as good as it gets. We wouldn't gain much by that. So here's, what do we do next? Great question, glad you asked. Let C sub I equal 5 nanofarads. Make them all the same. They're all 5 nanofarad capacitors, okay? So if we wanted to, we could just put all of these 5s in here. So 5 plus 5 plus 5 times 5 over 5 plus 5 plus 5 plus 5, because that's all we have in the bottom, plus 5 over here. So if you do all of the number crunching, you're going to get 8.75 nanofarads. Now, where does the nano come? Because the fraction part would have no units, because you'd have nanofarads over nanofarads. But that plus 5 is a plus 5 nanofarads, so you get it back. Okay. And so we would use this circuit reduction, which is based on just obeying the known laws of physics in terms of this new thing called capacitance that was defined and consistent with Coulomb's law. Now we could determine how much charge is going to be in the circuit given an applied voltage. How much charge are we dealing with? And then that would be useful for something else. And then we'll do the same sort of thing when it's resistors in the circuit. And we have current and voltage there. And then we'll pull them together. So these are all things that we follow up with after spring break. But we have to, what is a capacitor? What is capacitance? What does it do in a circuit? So I've shown that in the simulation. We're going to do more stuff in lab to pay attention to those patterns and whatnot.